Very warm greetings of the day to one and all present here. I am Geetika Agrawal and today I am going to give you a brief introduction about multilayered spheres in heat transfer. Before knowing about this, we need to know about some basic terms. One of these terms is steady state heat transfer. Steady state heat transfer means temperature of the substance do not change with time. Mathematically, it can be represented as dt upon d tau is equals to 0, where dt is change in temperature and d tau is change in time. On the other hand, unsteady state heat transfer means rate of change of temperature is not equal to 0, that is dt upon d tau is not equals to 0. Next is one-dimensional heat transfer. When the temperature of body changes with respect to one direction only, then the heat transfer is said to be one-dimensional. In such cases, temperature in the other two directions remains constant. When the temperature of the body changes with respect to two directions, then the heat transfer is said to be two-dimensional. In such cases, temperature in one direction remains constant. But when the temperature of the body changes with respect to all the three dimensions, then the heat transfer is said to be three-dimensional. In such cases, temperature varies in all the three directions. So now let's derive general heat conduction equation for spherical coordinates. For this, first we need to draw a diagram. So here we will draw three coordinate axes, that is x, y and z. And we will make a small portion of sphere on this coordinate axis. And now we will mark all the lengths and angles. And now we will draw this small part of sphere again without the coordinate axis and mark lengths again. This length is r d theta. This length is r sine theta d phi. And this length is dr. And now we will mark the planes. This is r plane. This is phi plane. And this is theta plane. So this is how it will be in different directions. In this direction QR heat will go inside and QR plus dr heat will go outside. Here Q5 heat will go inside and Q5 plus d phi heat will go outside. And similarly in this direction Q theta heat will go inside and Q theta plus d theta heat will come outside. Now we will write the volume of system, which will be the product of all these lengths and will be equal to r d theta into dr into r sine theta d phi. And we are calculating the equation for conduction, so Fourier's law will be used. According to this law, rate of heat flow, which is equals to heat flow divided by time interval, and it is equal to negative of Ka dt upon L. Therefore, heat flow will be equal to minus Ka dt upon L into d tau, where d tau is time interval. Now for r theta plane, phi plane will be perpendicular, so heat flow will be in phi direction. So using Fourier's law for Q phi, this will be equals to minus K dr into r d theta into dt upon r sine theta d phi into d tau. Let's mark this equation 1. Similarly, heat that will go out of the system will be Q phi plus d phi, and this will be equals to Q phi plus curl of Q phi with respect to r sine theta d phi into r sine theta d phi. Therefore, net flow will be Q phi minus Q phi plus d phi. Now substituting the value of Q phi plus d phi in this equation, solving this, we will get curl of Q phi with respect to r sine theta d phi into r sine theta d phi. Now substituting the value of Q phi from equation 1, solving this, we will get dq phi equals to k into dr r d theta into r sin theta d phi multiplied by 1 by r square sin square theta into d square t by d phi square multiplied by d tau. Let's mark this as equation 2. Now let's calculate heat flow in r phi plane. For r phi plane, theta plane will be perpendicular. So heat that goes into the system will be q theta and its value will be minus Ka dt upon L into d tau. Substituting the values, we will get q theta equals to minus K dr into r sin theta d phi into dt upon r d theta into d tau. Let's mark this as equation 3. Now the heat that will go out of the system will be q theta plus d theta, and this will be equals to q theta plus curl of q theta with respect to r d theta into r d theta. Net heat flow for this plane would be dq theta, and this will be equals to q theta minus q theta plus d theta. Now substituting the value of q theta plus d theta, solving this, we will get dq theta is equals to negative of curl of qr divided by r d theta into r d theta. Substituting the value of qr from previous equation, solving this, we will get dq theta equals to k into r d theta into dr into r d theta upon r square curl of sin theta into dt upon d theta with respect to curl of theta into d tau. Final equation after solving all this will be k into dr into r d theta into r sin theta d phi into 1 upon r square sin theta into curl of sin theta dt upon d theta with respect to theta into d tau. Let's mark this as equation 4. Now calculating the same for theta phi plane. Heat that goes in this plane will be equals to qr, and Fourier's law will be used. Now substituting the values, we will get QR equals to minus K into R d theta into R sin theta d phi into dt upon dr into d tau. Let's mark this as equation 5. Similarly, heat will go out will be equal to QR plus dr and will be equals to QR plus curl of QR with respect to R into dr. Net heat flow will be equals to dqr and will be equals to qr minus qr plus dr. Substituting the value of qr plus dr, we will get dqr equals to negative curl of qr with respect to r into dr. So now substituting the value of qr in this equation, dqr will be equals to curl of k r d theta into r sin theta d phi with respect to r into dt upon dr into d tau into dr. Solving this, we will get dqr equals to k into dr into r d theta into r sin theta d phi into 1 upon r square curl of r square dt upon dr with respect to r into d tau. Let's mark this as equation 6. Now considering effect of heat generator when placed inside the system. Heat generator due to heat generator will be equals to capital QG. Now capital QG is equals to small qg into volume of system into d tau. Substituting the value of volume, we will get qg into dr into r d theta into r sin theta d phi into d tau. Let's mark this as equation 7. Now the net heat flow through the system will be equals to density into dr into r d theta into r sin theta d phi into c into dt upon d tau into d tau. Let's mark this as equation 8. And we know that net heat flow through the system will be equals to heat generated due to heat generator plus heat flow through all the planes. So this will be equals to qg plus dq theta plus dq phi plus dqr. Now substituting the value of all these, we will get density into volume into c into dt equals to k into volume of system multiplied by time interval and whole multiplied by 1 by r square sin square theta d square t by d phi square plus 1 by r square sine square theta curl of sine theta plus dt upon d theta with respect to theta plus curl of r square dt by dr with respect to r into 1 by r square plus qg. Final equation will be equals to rho c dt upon d tau equals to k into 1 by r square into 1 upon sine square theta d square t upon d phi square plus 1 upon sine square theta curl of sine theta plus dt upon d theta with respect to theta plus 1 upon r square curl of r square dt upon dr with respect to r plus qg upon k. So general heat conduction equation in spherical coordinates is one upon r square sine square theta d square t upon d phi square plus 1 upon r square sine square theta curl of sine theta plus dt upon d theta with respect to theta plus 1 upon r square curl of r square dt upon dr with respect to r plus qg upon k equals to rho c upon k dt upon d tau. Let's consider some special cases about general heat conduction equation. For this, first we have to write general heat conduction equation for sphere. Let's take the first case, that is steady state condition. We know that at steady state, rate of change of temperature is equals to 0. Therefore, dt upon d tau will be 0. Now substituting this in general heat conduction equation, and the equation would be reduced to 1 divided by r square curl of k r square dt upon dr with respect to r plus 1 upon r square sine square theta k d square t by d phi square plus k upon r square sine square theta curl of r sine theta plus r dt divided by d theta with respect to theta plus qg equals to 0. Now coming to the second case, when there is no heat generator inside the system. In this case, qg will be 0 and the equation would be reduced to 1 divided by r square curl of k r square dt upon dr with respect to r plus 1 upon r square sine square theta k d square t divided by d phi square plus k upon r square sine square theta curl of r sine theta plus r dt divided by d theta with respect to theta equals to rho c dt upon d tau. Now third case, when the heat flow is one-dimensional. Let's assume heat flow is in radial direction Therefore, curl with respect to theta and phi will be equals to 0, and the equation would be reduced to 1 divided by r square curl of k r square dt upon dr with respect to r plus qg equals to rho c dt upon d tau. Now let's find the general equation at steady state without heat generator through a sphere. For this, first we have to make a diagram. Let's take a portion of sphere. Let's mark the radius and temperature. Inner radius is R1, outer radius is R2, and radius of the layer is R. Temperature of inner layer is T1, temperature of layer is T, and temperature of outer surface is T2. Now let's derive the equation. For this, first we have to write general heat conduction equation in spherical coordinates. And the equation is 1 divided by r square curl of k r square dt upon dr with respect to r plus 1 upon r square sin square theta k d square t divided by d phi square plus k upon r square sin square theta curl of r sin theta plus r dt divided by d theta with respect to theta plus qg equals to rho c dt upon d tau. Assumptions are steady state, therefore dt upon d tau will be 0. There is no heat generator, therefore Qg will also be 0. Heat flow is in radial direction, therefore curl with respect to theta and phi is also 0. And the equation is reduced to one divided by r square curl of k r square dt upon dr with respect to r equals to 0. This equation can also be written as curl of r square dt upon dr with respect to r equals to 0. Now integrating this equation with respect to r, we will get r square dt upon dr equals to c1, where c1 is a constant. This can also be written as dt equals to C1 upon R square dr. Now integrating this equation again, we will get T is equals to C2 minus C1 upon R, where C1 and C2 both are constant. Now taking boundary conditions, we know that at T is equals to T1, R is R1. Now substituting these values in above equation, we will get T1 equals to C2 minus C1 upon R1, and at T is equals to T2, R is equals to R2. Therefore, T2 equals to C2 minus C1 upon R2. Let's name this as equation 1 and 2. Now subtracting equation 2 from equation 1, we will get T1 minus T2 equals to C1 1 upon R2 minus 1 upon R1. From this we can get the value of C1, which is equals to T1 minus T2 divided by 1 upon R2 minus 1 upon R1. From equation 1, C2 is equals to T1 plus C1 upon R1. Substituting the value of C1 from above, we will get C2 equals to T1 plus T1 minus T2 divided by 1 upon R2 minus 1 upon R1 into 1 upon R1. Now substituting the value of C1 and C2 in T, we will get T equals to T1 plus one upon R1 into T1 minus T2 divided by 1 upon R2 minus 1 upon R1 minus 1 upon R into T1 minus T2 divided by 1 upon R2 minus 1 upon R1. This can also be written as T minus T1 equals to T1 minus T2 divided by 1 upon R2 minus 1 upon R1 whole multiplied by 1 upon R1 minus 1 upon R. Solving this, we will get T minus T1 divided by T1 minus T2 equals to 1 upon R1 minus 1 upon R divided by 1 upon R2 minus 1 upon R1. Where T1 is temperature of inner surface, T2 is temperature of outer surface, and T is temperature of layer. Similarly, R1 is inner radius, R2 is outer radius, and R is radius of layer. Now calculating heat conduction equation, we will using Fourier's law, which states that Q is equals to minus Ka dt upon dr. dt upon dr is equals to C1 upon R, which we have calculated above. Now substituting the value of C1, we will get dt upon dr equals to 1 upon r multiplied by T1 minus T2 divided by 1 upon R2 minus 1 upon R1. Now substituting this in above equation, we will get Q equals to minus Ka 1 upon R multiplied by T1 minus T2 divided by 1 upon R2 minus 1 upon R1. A is area of sphere and is equals to 4 pi r square. Substituting the value of A, we will get Q is equals to minus K 4 pi r square multiplied by 1 by r whole multiplied by T1 minus T2 divided by 1 upon R2 minus 1 upon R1. Solving this, we will get Q equals to 4 pi k T1 minus T2 divided by 1 upon R1 minus 1 upon R2 This equation can also be written as Q equals to change in temperature divided by 1 upon R1 minus 1 upon R2 divided by 4 pi k, where 1 upon R1 minus 1 upon R2 divided by 4 pi k is equals to spherical resistance. In case of multilayered spheres, this equation becomes Q is equals to change in temperature divided by summation of all the resistances. Now let's derive the heat conduction equation when heat generator is present inside the sphere. For this, first we have to write general heat conduction equation for sphere. The equation is 1 divided by r square curl of k r square dt upon dr with respect to r plus 1 divided by r square sin square theta k d square t divided by d phi square plus k divided by r square sin square theta curl of r sin theta plus r dt upon d theta with respect to theta plus qg equals to rho c dt upon d tau. In this we have assumed steady state, therefore dt upon d tau will be 0 and also it is one dimensional. Let's assume direction is radial, therefore curl with respect to theta and phi is equals to 0. Therefore the equation is 1 divided by r square curl of r square dt upon dr with respect to r equals to minus qg upon k. Now integrating this equation with respect to r, we will get r square dt upon dr equals to minus qg r cube divided by 3k plus c1, where c1 is integration constant. This equation can also be written as dt upon dr equals to minus qg r divided by 3k plus c1 upon r square. Let's name this equation 1. Now integrating this equation with respect to r again, we will get t equals to minus qg r square divided by 6k minus c1 upon r plus c2, where c2 is integration constant. Now in case of solid sphere, boundary conditions would be at r equals to 0, dt upon dr will also be 0. Now substituting this in equation 1, we will get c1 equals to 0. Now at r equals to capital R, t equals to tw. Substituting this in above equation, we will get c2 equals to tw plus qg divided by 6k capital R square. Therefore equation for sphere is t equals to minus qg small r square divided by 6k plus tw plus qg divided by 6k capital R square. Solving this, we get t minus tw equals to qg divided by 6k capital R square minus small r square. Now considering the same for hollow sphere, when inner surface is adiabatic. For this, boundary conditions are at r equals to r inside, dt upon dr will be 0, and at r equals to r outside, t is equals to t outside. Substituting these in above equations, we will get equation for hollow sphere with inner surface adiabatic. Now when outer surface is adiabatic, boundary conditions are at r equals to r inside, t is t inside, and at r equals to r outside, dt upon dr is 0. Substituting these values in above equations, we will get general equation in case of hollow sphere when outer surface is adiabatic. Now understanding what critical radius of insulation is. Thickness after which heat flow increases or decreases is termed as critical radius of insulation. We can find critical radius of insulation by substituting dr upon small dr equals to 0, where capital R is total resistance and small r is radius. In case of cylinder, critical radius of insulation is equals to k upon h, whereas in case of sphere, critical radius of insulation is equals to 2k upon h. Now coming to the concept of mean area. In case of variable area, sometimes mean area is used. It is different for both cylinder and sphere. In case of cylinder, mean area is equals to 2 pi L R2 minus R1 divided by log of R2 divided by R1, where L is length of cylinder, R2 is outer radius of cylinder and R1 is inner radius of cylinder. In case of sphere, mean area is equals to 4 pi square root of R1 and R2, where R1 is inner radius of sphere and R2 is outer radius of sphere. So this is it for topic multilayered spheres. Hope you all understood it well. Thank you so much.